We now discuss the solution of a problem on uniform convergence of the series of functions. And this is from the section analysis. This problem has appeared in CSIR NET National Eligibility Test held on 26th November 2020, and it is from the section B and it carries 3 marks. The problem is the series sigma n is equal to 1 to infinity minus 1 to the power of n sin nx by n power log n to the base e, where x belongs to the set of real numbers, converges. Option 1, only for x is equal to 0. Option 2, uniformly only for x belongs to the closed and bounded interval minus pi to plus pi. Option 3, converges uniformly only for x belongs to R other than the set n pi where n belongs to Z. And option 4, converges uniformly for all x belongs to R. We recall a test called Dirichlet test for uniform convergence of series of functions. What is that test? The test says that you have two sequence of functions, anx n is equal to 1 to infinity, bnx n is equal to 1 to infinity. If an of x n belongs to n and bn x n belongs to n are sequence of functions on the domain D, which is a subset of R satisfying first condition, sigma n is equal to 1 to infinity anx has uniformly bounded partial sums. That is, what is the meaning of that series has uniformly bounded partial sums? First of all, we take its partial sum. Capital A nx is equal to the sum of the first n terms of the series sigma akx. That is, sigma k is equal to 1 to n akx. That is the sum of the first n terms, which is called the nth partial sum, denoted by capital ANX. And mod of capital ANX is less than or equal to m, and m is independent of x and n. Then the given series sigma n is equal to 1 to infinity anx has uniformly bounded partial sums. These are the partial sums. Mod of that is less than or equal to m, which is valid for all x and n, and that will tell you the uniform boundedness. Condition, second condition, bnx tends to 0 uniformly on D. That is, as n tends to infinity, bnx tends to 0 for all x belongs to D. Condition C, that is, bn plus 1 x less than or equal to bnx for all x in D and for all n in n, that is the set of natural numbers. Now, then the series sigma n is equal to 1 to infinity, the product anx into bnx converges uniformly on D. Now, in this example, we take anx is equal to the numerator minus 1 to the power of n sin nx, and bnx is equal to 1 by n power ln n, that is same as log n to the base e. N belongs to the set of natural numbers, x belongs to the domain, which is the set of all real numbers in this case. We continue. We have sigma n is equal to 1 to infinity anx is equal to sigma n is equal to 1 to infinity minus 1 to the power of n sin nx, x belongs to R. Now, our first condition is we have to show that the series sigma n is equal to 1 to infinity anx has uniformly bounded partial sums. First of all, consider the partial sum. Let capital ANX is the nth partial sum of this series sigma k is equal to 1 to n akx. Then ANX is equal to sigma k is equal to 1 to n akx is minus 1 to the power of k into sine kx. Now this minus 1 to the power of k into sine kx can be written as sine of k in brackets pi plus x. You can see sine k pi plus kx is same as minus 1 to the power of k into sine kx. Expand this. K is equal to 1 sine of pi plus x plus sine of 2 pi plus x plus so on so forth sine of n pi plus x. Sine of pi plus x minus 1 sine pi x. Sine 2 pi 2x is sine 2x, and then minus so on so forth. At the end you will get minus 1 to the power of n into sine nx. So that is the expansion, and we recall a formula that what we have studied in trigonometry, and the formula says sin x plus sin 2x plus etc. sin nx is equal to sine of nx by 2 into sine n plus 1 x by 2 whole by sine x by 2. That's the formula that is available with us. Now, to get this sum, wherever there is x, you just replace it by pi plus x, you will get the sum there. So that will be equal to sine into sine of n in brackets pi plus x by 2 into sine n plus 1 into pi plus x by 2 by in the denominator sine of pi plus x by 2. So that is the result what we have written. And see the denominator, sine of pi plus x by 2 is same as sine of pi by 2 plus x by 2. Sine of pi by 2 plus x by 2 is cos x by 2. So write that. So the denominator becomes cos x by 2. We continue in the next slide. We have those series what we have considered, and we wanted to show that the series has uniformly bounded partial sums. We have considered the partial sum. The partial sum is this one. Now we have to talk about the uniform boundedness. So what we do is mod of ANX is equal to mod of sine n into pi plus x by 2 into sine of n plus 1 pi plus x by 2 by cos x by 2. When you take the modulus, it is less than or equal to mod of sine is less than or equal to 1. So less than or equal to 1 by mod cos x by 2. And cos also will take the highest value 1 when taken the modulus. It is less than or equal to 1 except for those values where cos of x by 2 is equal to 0. That means except at those values x by 2 not equal to 2r plus 1 pi by 2. So at these values of x by 2, cos of x by 2 becomes 0. And these are the odd multiples of pi by 2. And that is x not equal to 2r plus 1 pi where r belongs to z. Except these values, this mod of a and x is less than or equal to 1. It is true for all x belongs to r. Then we see what happens when x is equal to 2r plus 1 into pi where r belongs to z. So take the modulus of a and x. So modulus of a and x is equal to mod of sigma k is equal to 1 to n sine k in brackets pi plus x for x 2r plus 1 into pi 2r plus 1 into pi from here. So you write here, and now you see 2r plus 1 pi plus pi is 2r plus 2 pi. 2r plus 2 in brackets pi, and that will be equal to mod of sigma k is equal to 1 to n sine of 2k into r plus 1 times pi, and sine of, no, the multiples of 2 pi. Sine of 2 pi is 0. Sine of multiples of 2 pi is also equal to 0. So the summation will be 0, which is less than 1. So for this also, modulus of a and x is less than 1. So combining these two cases, including these exceptions, what we get is mod of a and x is less than or equal to 1, and which is true for all x belongs to R, and which is true for all n belongs to n. So the partial sums are bounded and uniformly for all x belongs to R uniformly, and for all n belongs to n. Thus, the sigma n is equal to 1 to infinity a n x has uniformly bounded partial sums. So this we have verified the condition 1 of the Dirichlet test. Now let's get into the condition 2. Notice that Bnx, we have Bnx is equal to 1 by n power log n to the base e, ln n, n belongs to n. And note that this is independent of x, and limit n tends to infinity of Bnx is limit n tends to infinity of 1 by n power ln n is 0 and holds good for all x belongs to R. So Bnx tends to 0 for all x belongs to R. Therefore, Bnx tends to 0 uniformly on R. That's the second condition satisfied. Now, we have for any natural number n, small n, n plus 1 is always greater than n. Therefore, n plus 1 to the power of ln of n plus 1 is greater than n power ln of n plus 1. And now ln of n plus 1 is greater than ln of n, therefore it is greater than n power ln of n, because ln of n plus 1 is always greater than ln of n for all n belongs to n. Now write the reciprocals. 1 by this, this is greater than, therefore it will become less than. 1 by n plus 1 to the power of ln of n plus 1 is less than 1 by n power ln of n. That is, this is nothing but bn plus 1x, and this is bnx less than or equal to, is strictly less than. So we have verified our condition. bn plus 1x is less than or equal to bnx for all x belongs to R. Of course, this is independent of x, therefore it is for all x belongs to R and is for all n belongs to n. That is the second condition. That is the third condition what we have verified. So by all the conditions are satisfied, by Dirichlet test for uniform convergence of series of functions, the series sigma n is equal to 1 to infinity, the product a n x into b n x, that is equal to the given series sigma n is equal to 1 to infinity minus 1 to the power of n sin nx by n power log n to the base e converges uniformly for all x belongs to R. Now let's look at our options. Our option 1 says it converges only for x is equal to 0. It converges uniformly for all x belongs to R. Therefore, option 1 is not true. And option 2, uniformly converges only for these values x belongs to the closed and bounded interval minus pi to pi, but it converges uniformly for all x belongs to R. Therefore, the option 2 is not true. And option 3 is also not true because it holds good, uniformly converges, holds good for all x belongs to R, other than the set consisting of n pi n belongs to z, but whereas it converges uniformly for all x belongs to R, therefore option 3 is also not true. Therefore, it converges uniformly for all x belongs to R, the option 4 is true. So thus option 4 is true. Options 1, 2 and 3 are not true. Our final answer is option 4 is true. So that is the discussion of the solution of a problem on the uniform convergence of the series of functions, and the question is from the section analysis. I hope that you have understood the solution of the problem. I wish you all the best. Thank you.